Ok, vamos começar então com a nossa terceira palestra do período da manhã. Após essa palestra, nós vamos ter um intervalo para o almoço e retornaremos às 14 horas. Nessa palestra do professor Paulo Sérgio Santos, aqui do Instituto de Química, ele é especialista em espectroscopia Raman. Como muitos sabem, e muitos também não sabem, o Instituto de Química possui um grande laboratório, um dos laboratórios pioneiros em espectroscopia Raman aqui no Brasil. E muito que é feito e tem sido feito é derivado do pessoal que estudou aqui no laboratório. O professor Paulo Sérgio, acho que é a segunda geração desse laboratório, então ele tem muita experiência e é uma pessoa que se dedica bastante a esse trabalho. Também tenta sempre correlacionar o trabalho experimental com o teórico. Então, professor Paulo Sérgio, obrigado.
Good morning, everyone. Thank you, Borin, for the introduction, for the invitation to be here. First of all, there are some apologies. After the first speaker speaking in a typical British accent, and Professor Riveros in a typical American accent, I'm afraid that now we are going to have a textbook accent. Second apology concerns the media of presentation. As you see, I'm going to use transparencies instead of the much more modern media. There is a reason for this. When our president took charge about a year ago, he said that during his term, everything should be done with transparency. So this is why I'm using it instead of the other way around. As you're going to notice, my presentation will be from the point of view of an experimentalist trying to tease or seduce theoreticians to get interested in the problems that I'm going to present. A very short historical presentation for those of you who are not acquainted with the Raman effect. Well, this is the man that discovered the effect. This is an Indian physicist, Chandra Shankara Venkatayulu Raman. What the effect is known after his last name. It was about 1928. He discovered the so-called inelastic scattering of light. And according to the history, it seems that he got impressed during a trip to attend to a conference in Europe. He got impressed by the color of the Mediterranean Sea. Just to give you this impression, and start his way back. You start to investigate in a regular way the scattering of liquids, scattering of light by liquids. He was a university professor in India, Bangalore. He was not a rich man. India was not a rich country. And nevertheless, he traveled by ship to Europe to attend the conference. So we can see how our profession of university professor got tremendously underpaid over the years. I'd like to start just mentioning a very simple diagram, presenting you a very simple diagram that gives you a cartoon impression of what is Raman effect about. We use a monochromatic radiation. Photons of H mu 0 interact with the molecule. This is an artistic version of a benzene molecule. And you have a scattered light with a frequency that is higher by S and is lower by S. in terms of an energy diagram, we have this transition from normally from the V equals 0, from the electronic ground state to a virtual state, and then the case to the first vibrational excited state. And of course, by energy conservation, you have these two possibilities. This is what you see in the spectrum. This is the central line, we will call Rayleigh line, elastic scattering, and this symmetrically distributed are the so-called Stokes and anti-Stokes that brings you the same information, but with different intensities due to the different Boltzmann population of the states. A more classical view, we have a sinus wave from the primary radiation, a laser, interacts with the molecule, and we have a modulated wave that is formed by the original frequency plus or minus any of the vibration frequency of the molecule. Again, a classical view, the variation of the electric field with the intensity of the laser. Here is the fluctuation of the bond polarizability of the molecule, and this is the scattered light that we detect as a beating of the vibrational frequency on the original laser line. Now let's skip this introduction and let's go directly to the 4 different regimes or 4 different types of Raman scattering. This is what we normally call the normal Raman scattering. Normal in the sense that the laser light photons have an energy that is far away, much lower than the energy of the first excited state. Then another situation when you use laser photons with higher energy. So we approach the excited state, but are not in fact in the excited state. This is so-called the pre-resonance Raman scattering. Then we have the rigorous resonance Raman scattering in resonance with discrete levels or with the continuum. The importance of these last 2 regimes comes from the fact that Raman scattering is a very inefficient process. You have scattering cross sections that are pretty low, on the order of 10 to the minus 30 square centimeters, and typically you have 1 in 10 to the 9 photons being inelastically scattered. And when you have this situation here, this scattering cross-section increases, enhances dramatically, sometimes by 4, 5, 6 order of magnitude. Then from the point of view of someone that is using Raman spectroscopy as an analytical technique, this is very important. But from a more fundamental point of view, there is a question. Why does the scattering intensity increase so much as we approach an excited state? These facts certainly have been known for quite a while. For instance, this is a very old work by Shorygin in Russia. At that time, lasers were not available. This is on the 30s or in the 40s. And what he did, he plotted the Raman intensity corrected for the 4th order of the exciting frequency as predicted by the classical electromagnetic theory, and excited the Raman spectrum with several wavelengths, possibly from a mercury lamp. And for different compounds, like Na means nitroaniline, NS, paranitroanisole, and so on, So what we see here, that even taking into account the force power dependence of the scattering intensity, when we are going to excite more and more to the UV, the Raman intensity of some bands, for instance, ZOC or NO2 or NS, increases. And obviously this means that we are approaching an allowing excited state of the molecule. Well, nowadays with the possibility of using lasers that can be tunable in a very wide range of frequencies, we certainly do not depend on a fortuitous coincidence with our source of excitation. We can obtain the optical spectrum, and looking at the optical spectrum, we can choose which frequency we are going to use in our laser to tune this region and look what happens to the intensities. In a way, what we do, we have an optical spectrum, this UV spectrum. This visible UV spectrum contains broadened vibronic information. For a molecule like benzene, that is one of the most investigated molecule from the point of view of resonance Raman spectroscopy, we know that we have some partial structure, at least in liquid phase, and this structure obviously contains information about vibronic transitions from the ground state to the excited state. But due to several broadening effect, we cannot obtain all these informations mode by mode. So that's why we used to say that the optical spectrum is not more or less than a convoluted multimode vibronic spectrum. Unless you have a diatomic molecule where you have just one vibrational mode. Any other case, you are treating with a multimode problem. Now the question is, how could we deconvolute this vibronic spectrum and separate them in several monomodes individually? Well, this is exactly what we do when we study, we investigate the dependence of the Raman intensity with the excitation frequency. Normally, a Raman spectrum of a polyatomic molecules have several bands, and what we want to know is how the relative intensity of such bands change as we approach, using our laser line, an excited state. This representation, Raman intensity, as a function of the frequency or the wave number of the excitation frequency for several vibrational modes, is exactly the separation of these multimode problems in a series of monomode problems. Just to give you an order of magnitude, and this is again benzene, or partly in Portuguese, but the important thing is the numbers you can see here. This is the Raman cross-section, and this is the excitation frequency of the laser. As you can see, as we move towards the UV, there is an increase in the cross-section, nothing fantastic. But when you go to a molecule like beta-carotene, and you excite just in resonance with its main pi-pi star transition, you have a dramatic increase in the cross-section. This is exactly what is called resonance Raman effect. And what we want to do is to understand how the nature of this excited state, the potential, affects the details of the Raman enhancement. Just to give you a real example, okay? This is titanium tetraiodide. That is a red color solid tetrahedral with a very intense charge transfer band indivisible, around 500 nanometers. Here we have a Raman spectrum of titanium tetraiodide excited with the green line of an argon ion laser. It's very unusual in a Raman spectrum the presence of overtones and combinations. This is much more common in the infrared. The Raman, this is an exception. As you can see here, you have a long progression in this NI1. NI1 is the totally symmetric vibration of the tetrahedron. 2 nu1, 3 nu1, 4 nu1, up to 12 nu1. And what should be the reason for that? The reason comes essentially from the shift of the minimum of the two potential curves, the ground state and excited state, along the normal coordinate that correspond to the mode that is being enhanced. So, if I could do in the reversed way, to represent these Raman profiles and have an algorithm that makes a relation between the Raman intensity profile and this delta, this shift, I could obtain informations about the geometric changes of this molecule along this normal coordinate when I go to this particular excited state. Obviously, at that point, I should mention that we would be much more comfortable if we could check this procedure by having a rigorous theoretical method that would give me the potential curve in the excited state along several normal coordinates. Thus, just to make it more easy to understand, this is the visible UV, the electronic spectrum of titanium tetraiodide. These are the points or the frequencies, the wavelength, matter of fact, of the laser that have been used to excite the Raman spectrum. A Raman spectrum should not change when I change the wavelength because I am measuring a difference. But what changes are the relative intensities. As you see here, this band with a star is a reference, is a band from the solvent. So when you look here, excited in the red, that is outside the absorption band, the totally symmetric modes here. Then I go to the yellow, then I go to the green in resonance. Look at the relative intensity of the reference. So if I make this normalization, this correction, this band should be perhaps up here. And now I have several overtones. So it's a drastic change just by the fact that I am in resonance with an allowed excited state. Obviously, for other molecules, like this species that is selenium-3, small polyatomic molecules, the effect of resonance is even more impressive. In a polyatomic molecule, it wouldn't be so impressive because the variations in the geometry are shared by many internal coordinates. Here you have just a few internal coordinates, so the relative change is dramatic. That is why we can see such a long progression in this selenium-selenium distance, because this is the coordinate that is more drastically affected when I go to the excited state. I can do this for more complex systems. For instance, for this coordination complex involving a platinum-platinum interaction. This is a much more complex molecule, but the chromophore is concentrated in this metal-to-metal transition. And that's why I see again such a huge progression that can allow me, for instance, to determine with very considerable accuracy the enharmonicities of these vibrations that for some applications are important parameters. I can go to even more complex systems. For instance, these are the observed and calculated excitation profiles for the one particular mode of the porphyrin ring mode of the oxymyoglobin. Although this is a very complex molecule, the chromophore is spatially limited. So is this moiety that is going to have the more significant changes in the internal coordinates. So we can see that even with more complex molecules, the agreement of the, not exactly calculations, this is just an algorithm. We use an input, the absorption spectrum, in a digital form, and from the absorption spectrum, you obtain the resonance Raman profile for several modes. What you cannot do in absorption spectrum because these modes are all convoluted in a single broad curve. Well, what would be the challenge from the point of view of trying to convince a theoretician to get interested in this problem? The Raman excitation profiles reflects the geometry in the excited state, the changes in the excited state, in the geometrical parameters as we go from the ground state to the excited state. Quantum chemical calculations in principle would permit us to obtain the potential curve, not only in the ground state, but also in the excited state. So if we could do this full cycle, would feel much more comfortable that our model, our algorithm, has a real physical significance. Concerning this point, let me just mention that at the moment there are two main theories to calculate Raman intensity. The first of them is the so-called sum over state picture. The second picture is the time-dependent picture. The sum over states is essentially comes from the Kramers-Heisenberg-Dirac relation for the transition polarizability tensor, and is a clumsy and awkward equation that involves a sum over a very large number of virtual states, so is of no practical use. Just from the conceptual point of view, we can understand this equation as a virtual absorption plus a virtual emission. So Raman process is a two-photon process involving these two kinds of excited states. Things becomes much easier when we are at resonance, because then this term is practically equal to this term. I mean, the energy of the photon is practically equal to the energy of the electronic transition. Then we can make a simplification, and the equation becomes this one. Well, at that point, as was already mentioned during this workshop, we have to use a diabatic Born-Oppenheimer approximation. And what we get is the two different terms for the calculation of the Raman intensities that are called A and B terms. A term explains the enhancement of totally symmetric modes. The B terms explain the enhancement by total symmetric and non-total symmetric modes when there are more than one excited state involved. This by far is the more common, and this by far is the more usual kind of enhancement involving the displacement of the potential curves along a totally symmetrical normal coordinate. This will be the two situations with a displacement equals 0 and with a displacement of the geometric coordinate different from 0. And as we can see from here, in this case, we are not expecting any kind of enhancement due to the orthogonal relation between the vibration wave functions. And in this case, they are not orthogonal anymore, and you have this long progression of Raman modes over a particular normal coordinate. Well, nowadays it's much more common to proceed to the so-called time-dependent picture introduced by Heller, Myers, and others in 1982. Just consider the A term that I mentioned. If we use these relations here, we can express the transition polarizability by this sum, or V is vibration, vibronic terms, and this is the energy of the laser. These are energy of the vibronic ground state, vibronic excited state, and this is the damping constant that responds for the lifetime of the excited state. Well, it's very easy to make this mathematical substitution, and when we do this, the polarizability becomes expressed by this relation, where the physical interpretation is relatively straightforward. What we have here, starting at time 0 in the back, at the vibrational level equals 0 in the ground state, interaction with light by means of the electronic transition moment interaction. This vibration wave function is transferred to the excited state. In this excited state, this wave function is not an eigenstate of the excited state Hamiltonian, and so this becomes a moving wave packet that comes to here, reflects and comes back, comes to here, reflects and comes back. At each time this wave packet passes in this Frank Condor region, you have an overlap with the vibration wave function of the final state. That's why if you plot this overlap, you have this maximum, minimum, and at the same time, this is multiplied by an exponential, negative exponential, because you have a damping of the excited state that is responsible for this continual decay until this wave function returns to the final state. If we plot this, the square of this, we have exactly what I showed you before in another form, that is the Raman enhancement profile. Raman intensity as a function of the excitation energy with several maximums and minimums that reflects the details of the potentials in the ground state and the excited state. For instance, one of the first applications of this algorithm was to understand the continuum resonance Raman scattering for bromine molecule. Remember that in this case we have a dissociative potential and a potential crossing here at this point. Here we have the continuum. And it was not very easy to understand the details of this resonance Raman experiment when you are doing excitation with the continuum. And from a conceptual point of view, it was not very easy to understand which kind of potential is reflecting the displacement of the minimum. So this is one of these complications when you are going to excited state that have a dissociation involved. Here is an illustration for the case of bromine. Okay? Here again, we have two excited states. One of them is dissociative. And here we have a clock in femtoseconds that show you how long does it take for the wave function, the vibration wave function, the wave packet, be transferred to the excited state, to walk here around, and then back. As we can see before it leaves, because it's a dissociative state. So we are speaking in terms of tens of femtoseconds. This also explains why the most important region is the so-called Frank Condon region, because this is the region where the overlap of the two-wave function is important. So here is where most of the Raman intensity is born. Well, this is a general case for a diatomic. Why, in the case of a diatomic, bromine, iodine, chlorine, we have, as a Raman spectra, a long progression of fundamental and the 10th or the 11th or the 12th overtone. Here we can see why. Because in this case, for very high vibrational quantum number of the final state, we approach the classical case where most of the amplitude of the wave function is at the extremes. So that means that we are going to have a significant overlap for a very long region of the potential. That explains why you have this long progression in case of diatomics. This is one calculation that was done with different potential curves for the pi1 singlet state of chlorine. So we have one potential number 1 that is believed to be the correct potential, and the other two that were on purpose displaced by about 2 picometers to smaller and larger antinuclear distance. And using this potential, for 3 different kind of formulas. This is Kramer-Heisenberg theory. This is steady state formulas, the time dependent, and this the experimental. And the difference by using potential 1, 2, and 3 for this case of dissociative potential is critically subtle. It's not very easy to tell which kind of potential is the best. That's one of the reasons why it would be much more comfortable if you could calculate from first principle this kind of potential. Let's skip that. So summing up this method, so-called time dependent, what we have, we transfer the ground state vibration wave function to the excited state. Here it becomes a moving wave packet. We can, from this dynamics of the wave packet, calculate the absorption overlap and the Raman overlap. From a simple Fourier transform, we can calculate the absorption spectra and we can calculate the Raman profile. These two things we can compare with experiment. And the adjustment, the fitting, depends essentially on the delta, the displacement along the normal coordinate of this mode for the excited state involved. Obviously, we have nowadays the possibility of obtaining the spectrum of the excited state directly, not just from the intensity as I showed here, because we can use pump and probe experiment. For instance, in this case, manganese pentacyanonitrosyl. This excited state is long-lived, so it's possible to pump with a pulsed laser and then to get the Raman spectrum of this species in the excited state. So here we have directly the vibrational frequencies of these species in the excited state. And in this case, obviously the question is the same. Do we have theoretical methods to calculate excited state property with the same degree of accuracy and confidence as we do in the ground state? Here is just the expansion of this in this region of the metal ligand and in the region of nitrosyl stretching. There is a class of molecules involving metal-metal bonds, as in this case of rhenium-2, bromine-8 anion, that absorbs in a region that allows you to obtain not just the time-resolved Raman, but the time-resolved resonance Raman spectrum. That is very interesting because you are going to obtain information about the second excited state. Although the signal to noise is not fantastic, with several accumulations and very fast detectors, you can obtain a decent spectrum of a molecule in the excited state. Again, the question is, how can we model these frequencies of these very high energy excited states using present methodology of quantum chemistry? So this is, our point of view, is also a challenge. And just to finish, an example from the literature, a recent one, involving this class of molecules. These are called metal dithiolines, and extended dithiolines. These kind of structures are highly delocalized. Metal in general is platinum, nickel, and palladium, and it can accommodate the metal in several excited states. One thing that is very peculiar of this species when we look to the absorption spectrum, depending on the size of the localization, this very strong band here, just look at the absorptivity. I'm speaking about absorptivities of 80,000, 9,000, 100,000. So it's a very strong absorber and at pretty low energy. The point is, when we start to increase the localization of these metal dithiolines, I think the record for this transition in literature is about 2,200. Wow, this is about 4,000 wave numbers. So you have an excited state, an excited electronic state, that is about 4,000 wave numbers above the ground state. First question, is this molecule or is this system to be considered as a valid system for a Born-Oppenheimer approximation? Because I have vibrations in molecules that are of the same order of magnitude of the electronic transition. Well, in fact, the authors present a lot of calculations using DFT for the frequencies, for the vibrational frequencies, for the energy, for the geometry, but nothing is mentioned about the geometry of the excited state or even the consequences of using the Born-Oppenheimer approximation for a molecule where the first excited electronic state is quite close to the ground state now. And depending of the particular compound in the series is comparable in terms of vibrational frequencies. So it seems that for most of the experimenters, Born-Oppenheimer approximation is something like a sacred cow. You never contest it. But I think now we have real systems in the literature. And every day we have a new example where the energy of the ground state, the excited state, is going closer and closer and closer to the ground state. And to my knowledge, I haven't seen yet a theoretical work trying to face this problem and to consider the very validity of the Born-Oppenheimer approximation in such case. So just a few cases to mention where is experimentalists doing resonance Raman spectroscopy. We would like very much to interact with theoreticians, not just doing the calculation for the calculation, but trying to highlight some conceptual problems that seems to be available, many examples in literature, and to my knowledge, I haven't yet seen a theoretical work trying to tackle this kind of problem.
Thank you very much for a very interesting and challenging lecture. I have, of course, 15 questions at least. Let me concentrate on one or two, maybe. But maybe first I can make a comment. Some of the systems you have shown here, I think are viable for theoretical treatment in the excited states. Others may not be. That depends on the system, but I think in some of them one could do some quite productive work. But I have a question to you in connection with that. Since your measurements are a good probe of the geometries in the excited state, you haven't shown us an example where you really have calculated the geometry or obtained the geometry of the excited state from your experiment. Is the information not enough to get that much detail that you can say that this bond length has increased by 0.05 angstrom, etc.?
Right.
Do you have such information?
Yes. Titanium tetraiodide, permanganate, nickel bisdiethylene. But let me be clear in this respect. The information we have is the delta along a particular normal mode, not all the normal modes.
Yes, of course.
So it's very partial.
When it comes to low-lying excited states, of course, what comes into my mind immediately, but you may be thinking about different types of excited state, because there's a lot of cases where you have near degeneracy in the ground state. I mean, you only have to think about dynamic Jahn-Teller distortion, which is a typical case where you have a non-Born-Oppenheimer situation, but this is not what you're thinking about here.
Well, as a matter of fact, if I had a little bit more of time, I should have mentioned this. We have been working for quite a while now with this kind of species. This is a terrible color. And same thing, so-called oxocarbon ions. All of them have the first excited state degenerate. And big surprise, in all the Raman spectrum of all these species, the strong modes, strong Raman lines, are not due to totally symmetric modes, are due to the so-called Jahn-Teller modes that couple the two degenerate modes. Well, surprisingly, there are many papers with some empirical calculations and more rigorous ones, but no one, to my knowledge, really tackled the problem of introducing the Young-Teller distortion in the calculation. I don't know if technical difficulties is too much, but I couldn't find any paper on theory of these systems. Because from the theoretical point of view, the first question is, are these systems aromatic or not? Then comes another question, what is in fact aromaticity? That seems to be a reason of dispute in the literature. So I think there is a lot of ground for exploring the problem of Young-Teller distortion in systems like this that are very highly symmetric. The spectrum are very easy to interpret, but I don't think any important theoretician was used to dedicate to this kind of problem.
I may comment on that because there is a class of processes in the theory in which these problems have been tackled with some success, and this has to do with photochemical reactions in organic molecules, where you have conical intersections, for example, and then you have to do non-Born-Oppenheimer dynamics on these systems, and that is really also done today to a large extent in many. But I don't think that we have done enough to try to do multi-electronic state vibrational spectroscopy, for example, or something like that. But certainly it could be done. I don't see any basic difficulties. Maybe technologically, well, not even that. I think it certainly could be done, as a matter of fact. But as you say, I also have not seen any such work. I don't know if Dan has any comment on it. Okay, thank you very much.
More stuff?